Well, I would like to, of course, thank the organizers for keeping the event and wish great recovery to Christophe and to Shirin also, by the way. I would like also to thank the lecturers for the very interesting and insightful talks that we had until now. I would like just to give my very little contribution to this nice event by reporting the work that was done in the group. It was devoted to electronic excited states of molecules, and in particular, we devote our time in trying to convert some linear algebraic considerations into physical considerations. Just to give a piece of context, I am among scientists who are interested in light-matter interaction, but not really from an energetic point of view, but rather from the perspective of the electronic structure and how it is reorganized upon light absorption, for example, light-matter interaction in general. I will introduce some tools and some tricks that are not approximations, but which help sparing some computational time. Obviously, you will see that the operations I will be depicting there are not time consuming, in fact, but when you have to repeat them a large number of times, for example, in the context of non-adiabatic dynamics, then sparing a few time for a given operation is rather interesting when you have to repeat it a large number of times. Just a few words about hypotheses for this talk. I will be dealing with n-electron molecular systems, and these n-electrons will be distributed into L-real valued spin orbitals. During the talk, I will use equivalently two notations for column vectors, either bold letters in the context of linear algebra or the bracket formalism in the quantum mechanical framework. Well, I will be dealing with single reference excited state calculation methods only. So the ground states considered there are single Slater determinants. When computing these Slater determinants, ground state Slater determinants, we also come with some extra orbitals. So in total, we have more than n spin orbitals. We have L of them, and they are, this is a collection of functions, and as such, we can define a vector space. They can define a vector space, and we can use them as a basis which spans this vector space. The vector space will be called the canonical vector space, obviously, and it's simply the set of linear combination of these canonical basis functions. Just a word to say that I will be dealing with a finite set of molecular excited states, molecular electronic excited states, because usually when you compute excited states of a molecule, you end up with a finite number of them. During this talk, I will be using one-body reduced density matrices and one-body density functions. Those will be simply related by the standard map, and since I will use a few of them, I will just not repeat the map each time. I just mention it there. It's just a standard map. It will be given always in the canonical basis, but this is not so important. Well, two definitions before really starting. An ordered list of real numbers can be given in decreasing or increasing order. This can have some importance. And well, I will just point this out by using a down arrow or up arrow. The first part of my talk, actual talk, is devoted to the qualitative analysis of the electronic structure reorganization of a molecule upon light matter interaction. And I will just give rapidly a few basics by recalling how we use the natural orbital theory from Perelov-Lovdin in the context of molecular electronic transitions calculations. So let's consider the difference and transition density matrix operators, the n-electron ones, yeah, the actual ones, and you trace them out by n-1 electron to end up with the 1 electron reduced difference and transition density matrices. These two objects are linear maps, and they map the space of 1 electron quantum states to itself. In fact, the canonical vector space that I depicted before is an invariant subspace in this linear map. So we can build the restriction of these linear maps on this invariant subspace, and this restriction as a matrix representation in the canonical basis, which is simply written this way. And we see that in the case of the difference density matrix, any of this matrix representation is belonging to the real symmetric matrix space, but it's not the case for the transition density matrices. At this point, I realized that if I continue this way, my slides will rapidly become unreadable. So maybe it's better not to discuss individual matrices, but to discuss generic matrices, or let's say any matrix and any operator of one kind. So let's, in what follow, use more soft notations for generic operators and matrices in the two cases. For the difference and transition density matrix operators and matrix itself, matrix representation. Good. We said that one of them was real symmetric, or any of them is real symmetric. So we can build an L tuple of their natural difference orbitals, which are simply the eigenvectors, and they come together with eigenvalues that are called occupation numbers. These occupation numbers are depicting the change in population of the natural orbitals, the natural difference orbitals during the transition. And from the negative populations, so the depletion of population, we can build a density matrix called the detachment density matrix. From the positive populations change, we can build the attachment density matrix. That's two new matrices that are interesting. They were proposed by Ed Gordon and co-workers 25 years ago, and they are very, very interesting. Now, let's see from the side of, let's look at the side of transition density matrix. This time, we have to perform a singular value decomposition, which means that it comes with left and right singular vectors. They are called natural transition orbitals this time, and they come with singular values. And each singular value is pairing a left to a right natural transition orbital. So they are really coming by pairs. That's important. Fine. With these two new bases, we can rewrite a one electron reduced difference density of matrix operator. And from now on, I will just say difference density matrix operator. That's much shorter. And speaking about shortening things, well, when you will have to compute a difference property, then you will see that in this basis, these things will become more rapid. That's also the case for the transition density matrix and operator. And you see that even if we have to construct it in two distinct L-sized bases, the operator itself is still spanning, is still defined on the canonical vector space in the end. Just two last interesting operators that were related in the literature more and more, so that's why I want to discuss them, is the transition hole and the transition electron operator, and they come together with a matrix representation. At this moment, I think it's interesting to summarize a bit the things. So we have on one side the difference, on the other one the product of quantum vectors, and on one side we get natural difference orbitals and detachment attachment density matrices. On the other side we get natural transition orbitals and hole and electron density matrices. Okay, what do we do with this? For this, I think it's interesting to look at a simple model, the CIS method, which I know is not widely used anymore for computing excited states, but it's a nice model on the paper for trying to understand what is beyond, what is behind these operators. So the case of CIS is very simple. It's the simplest ansatz you can imagine for an excited state. It's simply a linear combination of single electron promotion from the occupied spin orbital block to the virtual spin orbital block. And each of these single electron excitation is characterized by an amplitude, which is, it's these numbers that you can see on the right of this slide. And these numbers are stored into a rectangular array, X. And this array is part of the transition density matrix for the CIS method, which is a block matrix, and it is nilpotent. That's an important feature. The difference density matrix on its side is block diagonal. And you see that it's composed of two blocks. One is positive semi-definite, it's the southeast block. The other one is negative semi-definite, is the northwest block. And according to the structure of this difference density matrix, we immediately guess that the detachment and Hall density matrices will be equal, and they will be non-zero only in the occupied space, and the attachment and electron density matrices will also be equal to each other, and they will be defined only with non-zero elements only in the virtual block. Looking at this, you notice that we actually do not need to diagonalize the difference density matrix to extract eigenvalues and sort them with respect to their sign. We already know about this just by the structure of the matrix. So it spares the cost of a diagonalization. If the density matrices are equal in a given basis, then the density functions will also be equal in the same basis. So this could be a detachment attachment picture of a CIS transition, or equivalently whole electron picture of a CIS transition. And this could be canonical to NTO rotation or a canonical to NDO rotation as well, equivalently. And a nice feature in CIS for these natural orbitals is that in many occurrences, one singular value prevails. So for visualization purpose, it's rather interesting. And if we come back to this global picture we had before, in CIS method, things are getting simpler, and we have some relationships that are interesting, computationally speaking. Maybe too interesting, if you want my opinion, because I think that many developers and users made wrong generalities based on these equivalencies, and that's what we want to see here, and to go beyond CIS. If we go beyond CIS and, for example, get interested into time-dependent density functional theory, for example, then we do not only have excitation operators, but also de-excitation operators, and the amplitudes are stored in another vector. And this operator T, upper T here, is not a transition operator because it would lead to not norm conserving or number conserving states. It's just used to compute matrix elements, difference and transition density matrix elements. Yeah. Well, let's look at the structure of these matrices. The transition density matrix is not nilpotent anymore. It's still block matrix, but not nilpotent anymore. However, the difference density matrix is again block diagonal with a positive semi-definite block and a negative semi-definite block. So again, we can build the detachment and attachment density matrices without requiring any matrix diagonalization. And to my knowledge, this feature is still not used in code for computing detachment and attachment density matrices in TDDFT. But this spares time, actually. Okay? So we had this detachment attachment density matrices, but you remember we had also this transition Hall and electron density matrices. In equation of motion time-dependent density functional theory, they do not coincide. And in fact, if they do not coincide, the densities will not coincide neither. And in fact, the NTOs and NDOs pictures, so natural transition and natural difference orbitals pictures, are not identical. And moreover, I would like to add that in this case, we do not have a pairing between natural difference orbitals anymore. What does it mean? Does it mean that equation of motion TDFT representation of an electronic transition is equivocal, or does it mean that we have misused, or that some tools are misused? Every week, yeah, this is the global picture again, and here we see that we have some differences between CIS and TDDFT. And every week I see in papers people saying with TDDFT or other methods than CIS2, that the electron goes from this region of space, for example, here on the left of the molecule, and arrives at this region of space, here, for example, the right side of the molecule, upon light absorption. This is interpreting natural transition orbitals like natural difference orbitals, like if they can be interchanged, these interpretations. And I also see this with hole and electron densities. So the electron goes from this region of space to this region of space. But again, I said, is it an equivocal representation of a transition, or are some tools misused? Maybe I think that if I came to the basics before, it's also because of that. It's because I think that the underlying operators, the original operators, are not saying the same thing. They are not meant to deliver the same message. One is related to populations in density matrix theory. So when you take the difference between state density matrices, you have population differences. And this is related to the passage, to comparisons. So you compare properties between states, for example. The other operator is related to coherences between states, interferences, and couplings. So you can compute transition properties like transition dipole moments, oscillator strength, and these things, but it's not meant, I think, to compare states, compare the electronic structure of the states, and talk about the passage. By the way, the one transition density matrix misses multiple excitation and orbital relaxation effects because it is not designed for that. So if you wish to recover these effects, use detachment and attachment density matrices because it will be included. This closes the first part of my talk, and I will more rapidly go to quantitative analysis and start by defining the trace of the attachment density matrix. It's simply the sum of the positive occupation numbers of the difference density matrix. Since we did not lose or gain any fraction of charge during the transition, this quantity is also equal to the trace of the detachment density matrix. And this number is so important that we give it a symbol. We call it theta during the rest of the talk, and I will remind you this later on. Well, this is one number. It's the number of the number of charge that is involved in the transition. Compared to this, you have also the transferred charge, the net transferred charge that was proposed 9 years ago, and it's functional of the difference density in the real space. And in fact, 4 years after that, I proposed a proof to say that theta, so the trace of the detachment and attachment density matrices, is a higher bound to QCT. This is here at the bottom of the slide. We will come back to this later. Now, in the original publication by Head Gordon and co-workers about detachment and attachment density matrices, it was mentioned at the moment the possibility to relax the orbitals after computing the excited state. So this paper was mostly devoted to CIS method, but the way it depicts the orbital relaxation is similar for other methods. And well, in this paper, he said that relaxation of the orbitals has an impact on the eigen values of the difference density matrix. in the sense that it will lower the negative ones and increase the positive ones, as you can see there. He justifies this statement by the interleaving theorem for eigenvalues of symmetric matrices, and saying that the promotion number, so it's the trace of the detachment attachment, will be higher or equal to 1, which is the theta value for CIS method. But there is a hint about this, but no real proof. And to my knowledge, there has never been any proof to this, nor extension to other methods than CIS. So that's what I would like to suggest. Is it possible to prove this? Is it possible to extend the statement beyond CIS? And more generally, is it possible to provide an exact boundary value to the transferred charge? Because we gave a boundary value to the QCT before, but yeah, is it possible to generalize this to any difference density than what was proposed? What are the exact ones? Well, speaking about the interleaving theorem, well, I think it's a very old name for that is not used for decades, for the Cauchy's interlacing theorem, which is a perturbation of the spectrum of the B matrix you see there. How the spectrum of B is perturbed by adding, increasing the space of the vector space, let's say, the dimension of the vector space by 1, an increment of 1 unit. So you see here that you have a border Hermitian matrix, and it's partitioned with a principal submatrix, and on the southeast block you have a real number. And in fact, in these conditions, you have that the spectrum of the A matrix, so the big matrix, interlaces exactly the spectrum of the B matrix. That's the interleaving or interlacing theorem itself. It has some generalization, we will see this later, because in our case, the effect of the orbital relaxation is just the addition of this Hermitian matrix to the difference density matrix. So you get a partition matrix, again, a block matrix. And well, as I said before, we have on the northwest block a negative semi-definite matrix due to this lemma at the bottom of the slide. And on the southeast block, we have a positive semi-definite block. That's important for what follows. I'm almost done with the talk. And I suggest to introduce this other theorem, which is a generalization of Cauchy's interlacing theorem. It's the eigenvalue embedding theorem, or generalized Cauchy's interlacing theorem. It's for block matrices, again, Hermitian block matrices. And this time you see that the spectrum of B is in fact embedded into the spectrum of A. Yeah, this is interesting. What I did is, because this is related to Poincaré's separation theorem, I suggested to introduce a second theorem, which I wrote and proved. It's another theorem. It's not a corollary to the first one. It's really a distinct one, because you are considering another subspace there, and you see that you have majorization conditions instead of minorization conditions. So combining these two and considering the usual ordering that I gave before, U is standing for the tuples of unrelaxed difference density matrix eigenvalues, R for the relaxed ones. From the first embedding theorem, I get this relationship for some.
Sorry, Thibaud, you've been going for 25 minutes.
Already? Yeah.
You're able to finish soon.
I think I just need two more slides or 3 more slides. It's just a matter of 1 minute, maybe.
Perfect.
Yeah, thank you. And from the second embedding theorem that for which I gave a proof, this will be published soon. I have other relationships, other inequalities. So if you combine them, you get this inequality between traces of detachment attachment density matrices. Well, so yes, we can prove this statement, and we can extend it also because the only necessary and sufficient condition for this statement is that the difference density matrix is block diagonal, with northwest block being negative semi-definite and southeast block being positive semi-definite. So it also extends to Bethe-Salpeter, TDDFT, and so on. Very last thing, can we provide exact boundary values to the transfer charge? Well, again, considering this matrix and its spectral decomposition, we can build a detachment-attachment density matrix related to the unrelaxed relaxed state passage. And this quantity will be useful right now because I will use a third theorem from linear algebra, and in fact, not exactly the theorem itself, but a corollary of it, which gives a majorization condition between the tuples of eigenvalues of two Hermitian matrices and their sum. So A and B are summed into C. And I use this inequality and I apply it to my case, my special case, to give a higher boundary value for the relaxed trace of the detachment attachment. So yeah, since it was stated by Fürch 9 years ago that if we had the exact functional and if we believe in the quantum hypothesis, we would have the exact difference density matrix, then we would have the exact number for this upper bound. So yes, we can also provide an exact boundary value for the transfer charge. And this leads me to my conclusion that we can do these things. And I will just thank people with whom I have the chance to work for these years and tell you about just a software that was released last year and which is related to this reorganization of the electronic structure. I thank you for your attention.
Thanks. That leaves just about 2 minutes for questions. The paper is open to questions, if there are any. I have a very general question. First of all, the comment is that it's so nice to see that work by the great mathematicians like Cauchy and Poincaré are useful to you even now. And the question is, where can I find references to the original work?
Well, all the relevant references will be given on my website. My website is given, the address of my website is given in the abstract of my talk in the book of abstracts. So all the relevant references will be given there. And the Cauchy's interesting theorem is quite widespread in linear algebra. You can find it in many textbooks. I can recommend you the matrix analysis of Bassia, Bassia. And well, it's a consequence of the Courant-Fisher min-max principle. That's how you can demonstrate a few things there. So I would say many of these theorems are basic results now that are taught in graduate mathematical courses, I would say.
Okay, I see no further questions and we're at 11:30. So let's thank Thibaud. And in view of the fact that Shirin